Welcome to our problem session. So today we have this interesting problem. This comes from energy conservation concepts. So here is a track like this. There's a loop here, and we're supposed to take this track is frictionless, and we let it go at some point at some height from this bottom part. So this one is supposed to be at this one is same level as this, same level as that. So we are supposed to find, if let go at rest here, so this block, and then we're supposed to find that as it goes around, it does make it all the way around. Of course, if height is not too high, it might just fall off here, but it just makes it around. And there are two conditions, like condition 1 and condition 2, that we're supposed to examine. Okay, in the condition 1 is it just barely makes it. Doesn't mean v min is 0. Okay, it is going at some speed that if v here, the top, v top is less than v min, it's not going to make it, it's going to fall off. Okay, if not going around, so we will not go around. Okay, so you need more than that. You can have as much as you want, more than that. Okay, it can go very fast. The faster it goes, the more the track pushes on it. All right, so at some point the track will push, so that the push on the block is as much as the weight of the block. Okay, I didn't say mass is m. Okay, you don't really need the mass because mass will cancel out. All right, so what do we need? The formula we need is, if this is the y-axis, then if this is the point whose coordinate is y, at this level anywhere coordinate is y, maybe this x-axis if you want to call it. So this is like a east, maybe it's north, and this is up, and so from here is y-axis. So at this level, potential energy due to this gravity, not the force of gravitational from Earth, that's different, but U due to little g is mgy. I like to say mgy instead of mgh. I want to make sure that the y is positive here and y is negative here. So this point, this plane here, this flat plane, horizontal plane, this is called u equal to 0 reference. So always this formula that you're going to write down is with respect to some reference. Okay, all right, so that's one bit of information you need. Another bit of information you need is, because there's at no point there is any other force which is non-conservative. So if you look at any part of the track, so when it was over here, it went from here all the way here. So this is the point, initial point, and this is the final point we're looking at, examining that. So this is the path that object took. At any point, you can see over here there's a force of gravity, and there's a normal force and weight. So this is a weight. W is conservative, and normal n, you would say is not conservative, but actually work by normal force will be 0. Now why that will be 0? So if this is the path, normal will be 90 degrees to the path. So if this is the vector dr, then n is perpendicular to dr. That will means n dot dr will be 0, and the work by the normal force, some initial to final, normal force dot dr equal to 0. So this is going to be always 0. Okay. So and this is a conservative force. Then use potential energy to account for the work. We've already explained to you earlier in previous video that the work by a conservative force is equal to minus potential energy at the final, initial to final, is potential energy initial. So this is just change, negative or change in potential energy is the work done by conservative force. So that just led us to have kinetic energy plus kinetic energy, potential energy initial. This combination is equal to kinetic energy final plus potential energy final, because work non-conservative is 0. So that was the conservation of energy, and it's going to happen here because of this fact. Now let's examine. Now we know 1 and 2. This problem is really not that difficult once you look at it that way. So if this initial, this final, and on this path, I don't need to worry about the work, because potential energy will just relate this with that. So if you say this is the xz plane of this guy, and let's call this y-axis. So this is y initial, and this is y final. So kinetic energy final minus kinetic energy initial will be potential energy initial minus potential energy final. I'm just was thinking like that over there. So if the speed we need is v min here and v0 here, so half m v min square minus 0 equals to pe. The h is actually not given. We're supposed to find out the h. So find the h. So let's see where we go with v min, how v min is related to the h. This should give us that. Potential energy initial is this yi, which value is h, which is positive. So mgh, what is potentially final? We have to have this height. This is 2r, so y is 2r. Y final equals to 2r. Mg times 2r. So if I know v min, I can get h. So let's just write down the m's. As I was saying, m cancels out, and we can write gh equals to half v min square plus g2gr. So this would be the answer for the h, or if we divide by g, So this will be the answer for H if I know what V min is. How do I get V min? Well, let's look at how can I get what the V min has to be here. Well, if it's going to go around a circle, so over here is a circular motion. In circular motion, it can be if the speed is v here, then we would let's draw it out, okay? So this circular motion, and if it's over here, speed is v over here, v min. Let's vm just for short, and it can be changing, the speed can be changing, but at this instant it's over here. So if I were to write F equals ma, I should be able to this, because circular you can do tangential, so there is forces on it. Mg is this way, and block would be pushing against the track, and the track would push back. So there will be normal this way. We don't know how much normal there is. So, and there are no friction, so there are no forces along that is zero. So this is all the forces there is. So if we look at acceleration, if you use a coordinate which is based to the center here, another coordinate, right? So this will be the radial, little r distance from this radial. So this is radial coordinate going up, and this will be theta head direction. So theta head direction, there's nothing happening, right? So at that instant, if you go a little bit later on, then there is a so if you were to look at, and the reason it slows down is the gravity is speeds up, it slows down, it's coming like this, speeds up, comes like this. If you look at over here, if you look at the gravity here, and then this is the radial direction, our head direction, and this is the theta head direction. So if this is the angle theta, then you have this mg, the n is pointed that way, and mg is pointed that way. Mg has both radial and tangential component, right? Mg has both radial and tangential component. Okay. But over here it's just a tangential, just radial component. So, and this is a Vm square over r for this, and this is the radial direction. So if you look at A, is Vm square r minus r hat. The direction is towards the center, okay? And you have both n and mg towards the center, so you can do formally radial direction, radial equation of motion, radial F equals ma. That just turns out to be n plus mg is mvm square over r. But if you can just barely make it, meaning I want the smallest value of this, this is fixed. When would this be smallest? When v at the top is, well, when n is the smallest, and n here is the positive value, right? So n smallest will be 0. So n equal to 0 corresponds to v min. So v min from here is square over r equals to g, from this equation setting n equal to 0 over here. And so Vm square is just gr. Now let's go back there and rewrite over here. So H is equal to 1 over 2g v min square 2g 2r 2r g got cancel out. Okay, so if I from a this is v min square over g is r, so this is 1/2 r plus 2r, so just 5 over 2r. So that's the answer, just for barely making it. Okay, so this is the answer for one, answer for this guy, just barely making it. Now the second part says, what if I want the block to push equal to its weight, push up equal to its weight? Well, push up, if the block is pushing up, then the track will push back. That's the normal. So this actually is a weird language to say. This is a weird language, and it's say by Newton's third law. All it's saying is, I give you the normal. Normal is no longer 0. Normal is mg. Maybe I can just make it even more specific. Twice its weight. Let's call it twice its weight. So normal is 2 mg. I want the how high this should be, how high it should be. So if I let go from here, it goes like this, and when it comes over here, it pushes on that twice its weight. Okay, let's do that one. Twice its weight. So if I so this, nothing changes over here. Instead of v min, it just becomes just some v that I will need. Okay, that v will still be this formula. It still be radial, but this n, rather than being 0 and giving me the answer, this n is 2 mg now after my change. So this will be, this equation will transform for number 2. It transformed to 2 mg plus mg mv square over r. And so v square over g will be 3r. So now here h will be 1 over 2g v square over 2r, and v square over g is 3r, so 3 over 2r plus 2r, 7 over 2r. Okay, so you have to let go at this height for it to push again. So you can see, you can actually solve it for whatever different heights you are thinking. You can say, well, what if I want to push it 10 times the weight? 10 times its weight. When you go through there, and then everything will be same. Everything will be same, except that over here it will be 10 times. So it's going to be v square over g will be 11r, and that will end up at h equals to 11 over 2 plus 2r, 15 over 2r, etc. Okay, that was a pretty interesting and simple problem, but illustrates an important concept. The concept about the minimum and when the normal have to be 0 and such, and hopefully you got something out of it. So if you like this kind of explanation, think of subscribing to this channel. Tell your friends, tell your teacher maybe. I try to post approximately one a day, and I'll continue to post as long as I have time. So hope to see you in another video. Okay, take care. Bye.